So the first thing we'll do when we're now pushing the boundaries from what we know about dot products to what we are going to know about this new operation that we're going to call an inner product. The first thing we do is change notation. We're not going to use transpose. That really is something that belongs to matrix analysis. Instead of a dot product, what we'll use is a pair of angle brackets. So I have an angle bracket here, an angle bracket here, and a comma in between. And that notation is what will replace the dot product of the function sine x with the function 1. We'll just use angle brackets like that. So that in the denominator, instead of a transpose, again, what we have is the inner product of sine x with itself. So that's notationally what this is going to look like. Now I'm going to put a definition up here that we're not going to do much with because it's a very general definition. But it's the definition that gives the dot product of vectors and this product that we're going to use with functions, it gives it its common set of properties that make them useful in projection. So the definition goes as follows. Let V be a vector space. So not specifying what the vectors are. They could be vectors in Rn. They could be functions in an appropriate space of functions. Whatever. V is a vector space. Then we're going to define what it means to be an inner product on V. And this is a generalization of the dot product in Euclidean vector geometry. So here are the properties that it must have. First of all, it needs to be a function which takes two vectors as input. Right? So sine x and sine x are one vector and another vector in R2 if we're using a dot product. It needs to take two vectors as its input, so its domain needs to be the cross product of V with V. And its codomain needs to be a scalar, right? It needs to produce for us a scalar quantity out of this. So for our purposes, we're going to think about inner products that give us a real number out of it, a real scalar. We can define a similar notion for when that field is a field of complex numbers, but it needs to be scalars. And we're going to use these angle brackets as our notation for this inner product. So first of all, an inner product on V is a function which takes two vectors, two elements of V, and produces for us a scalar quantity, which we're going to consider to be real. And then we need to attach some properties on top of it, so such that the following conditions hold. Not every function that takes in two vectors and spits out a scalar is going to qualify. We need a few things. First thing we need is symmetry. What do you think symmetry means that you know is true about the dot product? What does that suggest? Yeah, it's essentially a commutative property. Right? That V and W, if I take their inner product, if I were to reverse the order of V and W, the results should be the same. And the hidden quantifier here is that this needs to be true for all V and W in my vector space. So symmetry just means that we can transpose the order of the operation and we get the same result both times. So that's the first property. We know that's true for dot products of vectors. It will also be true for our inner product of functions that we're about to use. So that's one. Here's a concept called bilinearity. This, I think, may be the most restrictive of the conditions that we place on this. It tells us that we can't just define this function in any way that we like. We need to define it in such a way that it is linear both in its first argument and in its second argument. That's where the bi part comes from. It needs to be linear in the first and second arguments of it, which means nothing more than if I have three vectors, v, w, and x, let's say, then if I add w and x in the second entry of my inner product, then what do you think I'm supposed to get? If I add and then take the inner product, I should get the same result as if I take the inner products and then add. So addition can be split out in the second argument. But then the other part of linearity is that that also needs to happen for a constant multiple. So c times w is equal to c times the inner product of v with w. And the quantifiers here that I should make sure to have are that v, w, and x range over all possible vectors in the vector space, and then c ranges over all possible scalars. So just that this inner product has to be a linear function. If I add or if I multiply by scalars, in other words, if I take a linear combination of vectors and then subject that combination to an inner product, I should get the same result as if I took the inner products first and combined them together in the same combination. This really restricts the kinds of functions we can use as inner products. It's probably also one of the more irritating conditions to actually check a lot of times, if you're checking whether some arbitrary thing is an inner product. But bilinearity is a big one. And the last condition that we impose upon inner products is a condition called non-degeneracy, which is a mouthful. And the non-degeneracy condition tells us that if I take the inner product of a vector with itself, let me actually pause here for a second and ask you, in vector calculus, when you take the dot product of a vector with itself, what are you getting? What kind of a quantity is that? V dot V. Yeah, what does it measure? It measures the magnitude of the vector, or what we might call the norm of the vector. So if I'm measuring the magnitude of a quantity, what kinds of numbers do I get? What kinds of numbers am I guaranteed to get? I'm guaranteed to get numbers that are greater than or equal to 0. Right. So that's what we require. That when I take the inner product of a vector with itself, the result has to be non-negative, first of all. So that's part of non-degeneracy. Anytime I take the inner product of something with itself, the result is non-negative. But there's more to the picture. And that more is this. That not only should this quantity be non-negative, but also, let me ask the remainder of this in the form of thinking about vectors in R2 once again. If I take the dot product of a vector with itself, v dot v, and I get something which is equal to 0, so if the dot product of a vector in R2 with itself is equal to 0, what does that tell you about the vector? In the xy plane, what vectors have 0 magnitude? The 0 vector. And so that's the yet more restrictive requirement that we place here as well. So the inner product of a vector with itself is non-negative, and v dot v, if you like, is equal to 0 implies that v is the 0 vector. Maybe I'll put vector symbols over that just to emphasize the difference here. So the only vector whose inner product with itself is equal to 0 is the 0 vector itself, for whatever interpretation the 0 vector has in the vector space that we're defining this inner product on. So these are the characteristics that make an inner product have the properties that it needs to have to behave the way that it behaved in the first part of the semester, like it does in vector calculus and linear algebra with vectors in Euclidean spaces. Any other thing we can define that does this stuff, we'll still be able to define for us notions like projection, even if our vector space is something much different than R2 or R3.